What's up guys, it's Simon Fiaz and today's video is on AS level chemistry in May 2019 in this case, paper 1. Explain why fluoride is larger than a sodium ion. And it says Na plus and F minus have the same electron configuration. Fluoride ion has fewer protons / lower nuclear charge, so weaker attraction between nucleus and outer electrons. There's a weaker attraction between nucleus and outer electron. What happens? Well, it's going to be a bit bigger, atomic radius, and larger. So yeah, the fluoride would be larger. Fluoride has fewer protons / lower nuclear charge, weaker attraction between nucleus and outer electrons. Experimental restriction and bonding. Another point of sodium fluoride is high electrostatic forces of attraction between oppositely charged ions and lots energy needed to overcome these forces. 1.3 name the type of bond form and HF. And now I just want to say one thing. Anytime it really says name the type of bond form when something reacts with something, 9 times out of 10 is coordinate bond. In this case, obviously, it's going to be coordinate bond or dative covalent bond, whatever you want to call it. So yeah, coordinate bond. That's the easy part, spotting it. Once you've done like seeing this type of question a lot. So it's a coordinate bond, but explain how the bond forms is probably the more difficult part. It's the idea that hydrogen fluoride gains a proton to get H2F. A lone pair of electrons is donated from F. Question 1.4, draw the shape of SbF6 minus ion and the H2F plus ion. So there we go. Square brackets, negative charge, square brackets, positive charge. Now the SbF6 minus ion, SbF, F here, F here, F here, and F here. 6 bonding pairs, no lone pairs. So it's going to be octahedral. The naming of the shape. H2F plus hydrogen bonded to fluorine, and then it's going to have, no, it's not that, it's the other way around. I've got 2 hydrogens, only 1 fluorine, so I'm going to remove that. So you got F, hydrogen, and fluorine is in group 7, isn't it? Yeah, fluorine, iodine, and all that, and chlorine. So then it's going to have, it's bonded to 2, 7 minus 2, but it's also got a positive charge, so we minus 1. So 7 minus 2 is 5, so it have 5 pairs, 5 electron pairs, but then minus 1 because positive charge, then it's only got 1, 2, 1, 2. So 2 lone pairs of electrons. In the name of shape, 2 bonding pairs, 2 lone pairs. So it's going to be bent. Use the data table 1 to calculate a value for the bond density of a CF bond in the product. Coordinate bond, lone pair of electrons is donated from F, drawing the shapes octahedral and bent. So bond enthalpy, I'm giving me bond enthalpy is energy required to break bonds minus energy released when new bonds are formed. I know delta H is minus 179. I really don't like the mean bond enthalpy questions. There was one in my mock, and it was like 3 marks, was it? Or maybe, I think it's 3, maybe 4 or 5, I'm not sure. But Yeah, I didn't get it correct. Let's just say that. So minus 179 equals energy required to break bonds. So HC bond 412 plus 837 plus CH bond 412 plus 562 times by 2 HF bonds. Energy required to break bonds minus energy released when new bonds are formed. Well, I've got one CH, another CH, another CH, so that's 1, 2, 3, another CH, 4, another CH, 5, so 4, 1, 2 times by 5 plus a carbon-carbon bond, which is 3, 4, 8, plus your CF bond, which you're trying to find, which is just, oh, no, I've got 1, 2, 3, 4, only got 4, that's a C, that's an F. Plus 3, 4, 8, that's an F, I thought it was a H, so then plus 2y. Now this is the most difficult part, rearranging and not making any silly mistakes, addition or subtraction errors. It's usually the, subtraction. So minus 179, 1661, and 1661 plus 562 plus 562, 2785. So minus 179, 2785 minus, well, I've got 4 and 2 times by 4 plus 348 carbon-carbon bond minus 1996 plus 2y. Well, let's do that. 2785 minus 1996, 789. So minus 179 equals 789 plus 2y. But remember, that's 789. But what I'm doing, energy required to break bonds minus energy released when new bonds are formed. This is energy released when new bonds are formed. So 2785 minus this whole thing. So 2785 minus 1996. Or what I would actually do, which I think is better option, is put round brackets around them, and then think about like this minus is just a minus 1. So then I'm going to times that by minus 1, so that's minus 1996, and that's what I get, 789. And then that's also minus 1, so that's going to be minus 2y. Otherwise, if you just treat it as positive, you'll get negative what you're supposed to get. So you get a negative y, so plus 2y, 2y minus that, so therefore 2y is 789 plus 179 divided by 2, 484. Question 2.1, describe how the molecules are ionized using electrospray ionization. So sample is dissolved in a volatile solvent, injected through nozzle/needle, a high voltage. Each particle gains a proton/a H plus ion. So some electrospray ionization, sample is dissolved in a volatile solvent, injected through nozzle/needle at a high voltage. Each particle gains a proton/H plus. Sample is dissolved in volatile solvent, injected through nozzle/needle at a high voltage. Each particle gains a proton/H plus. Give the formula of ion that reaches detector first in the times by mass spectrometer. So the one with the lowest MR, which is just going to be definitely not going to be that one. No, it's going to be that one then. Detector first, yeah. So C3 H5 O2N. But the thing about electrospray ionization, the H plus ion. Each particle gains a proton, H plus. Sample dissolved volatile solvent injected through nozzle at heat slash needle. Sample dissolved volatile solvent injected through nozzle slash needle at high voltage. Each particle gains a proton. So it's going to be, I'm going to add a proton. So then say H plus. Or I could say C3H6O2N plus. But this is better, I think. C3H5O2N and then H plus at the end of it. Give an equation for process recursion ionization of a germanium atom, electron impact. This was electro spray, so now I'm in a different ionization. So in this case, it's going to be, the thing about electron impact, it's really similar to, like it is to the first ionization. So go from there and use information to calculate mass in grams of 1 mole of these germanium ions. Okay. So mass equals 2ke divided by v squared, and velocity, that's the first equation. Then the second one, velocity is distance divided by time. So it's going to be 96, well, that's centimeters on a meter, so 0.96 divided by 100, and divided by the time, which is at 4.654 times by 10 to the power minus 6 seconds. And then that's the velocity, so then I substitute in there squared, 2ke, 2 times by 2.438 times by 10 to the power minus 15 divided by my answer squared. So it's going to be 2 times by 4.654 times by 10 to the power minus 6. That's the, no, that's not, no, that's time. So 2 times by 2.438 times by 10 to the power minus 15 joules kinetic energy divided by the velocity, which is then 0.96 divided by, I don't know what's going on, 0.96 divided by the time, there we go, 4.654 times by 10 to the power minus 6, and that's all of that squared. Then I get the mass as 1.15 times by 10 to the power minus 25 kg. How do I know it's in kg? Because it says it here, mass is in kg, and you should know that for the time-of-flight mass spectrometer. I want the mass in grams, so then I need to times by 1,000. When I times out 1,000, that just becomes minus 25 to minus 22 grams, and then I times by L, which is Avogadro's constant. Why else would they give it me in the question? There you go. So it's going to be 1.15 times by 10 to, I forgot to times it by 1,000. Times by 1,000, then times by Avogadro's constant. And then there we go, I get 69 grams. And then the mass number of the ion, what's that going to be? 69. So no trick there. But you must have a whole number for the mass number. Yeah. 69 grams, and then mass number is 69. Not for 5 marks, that's pretty nice to be honest. It's just this unusual mass in grams, 1 mole, and you time by Avogadro's constant, then state the mass number. Well, it's just going to be the mass in grams of the 1 mole of that. Question 3, complete full electrical configuration of a chromium atom. So, chromium, data sheet, and I know chromium atom Cr has 24 electrons. 24. So it's going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Alright, now let's count. So I've got 2 plus, I'll just put my calculator. 2 plus 2 is 4, plus 6, plus 2, plus 6, plus 2. 20 electrons, so I need 4 more. So 4s2, and then 3 more. One s two, 2s2, 2p6, 3s2, 3p6, 4s2, 1 more, and 3d4. Yeah, 3d4. But the special rule with chromium and I've got the other one. Clearly haven't reviewed this topic in a while. Well, yeah, you do need to. Is chromium and something else? I'm pretty sure. Yeah, but they have a special rule, and what happens is the d orbital would rather be full because d electrons, right? So 5 electrons. So what happens is that becomes 4s1, 3d5. Well, yeah, 4s1, 3d5. That's what happens. And every time you see chromium or another one, draw it out normally and then realize special rule. So it goes to the 3d orbital because 3d is actually of slightly lower energy than the 4s orbital. An atom has 2 more protons and 3 more neutrons than an atom of 52 Cr. Deduce the symbol including mass number and the atomic number for this atom. So 2 more protons than 52 Cr. 52 Cr. Well, it's got 24 protons. I'm going to write that down. It's 24 on the bottom. So it's going to have 26 H pluses, protons, and 3 more neutrons. Well, number of neutrons in this case, 52 minus 24, 28. But 3 more neutrons, so it's going to have to be 28 plus 3, 31. Then 26 plus 31, 57. So it's going to be 57, 26 for this atom. Iron. Because remember, it's the number of protons that determines what it is, not the number of neutrons. So 57, 26 Fe. Determine the percentage abundance of fourth isotope. So well, I'll just say I'm trying to show by calculation mass number is 50. Well, that's just going to be let it equal to x. The abundance though, well, it's going to be 82.8 plus 10.9 plus 2.7 and then 100 minus my answer, 3.6%. And I know the relative atomic mass is 52.09, so I can say 52.09 equals 52 times by 82.8 plus 53 times by 10.9. And this question example how they can involve algebra in it. But in this case, it's not too difficult. It's a bit more difficult questions of relative atomic, well, percentage abundance, and you've got algebra, and you need to 2x or something else minus x. So plus 3.6x over 100. That goes there, so you get 5209. And then what I do is I do 52 times by 82.8 plus 53 times by 10.9 plus 54 times by 7.7, and then I do 5209 minus my answer. Wait, 52 times by 82.8 plus 53 times by 10.9 plus, yeah, that look, I thought that was 7.7, that's 2.7. And if it was 7.7, they get a negative value, then that won't work. 5209 minus my answer, and then divide by 3.6. And I get 49.97, so therefore, yeah, 50%. That's equal to x, therefore x equals 50, the mass number. To reduce oxidation of chromium in this sign, well, oxygen minus 2 times by 7 minus 14, then that needs to be plus 6 then, because plus 6 times by 2 is 12, 12 plus 12 minus 14 minus 2. Iodide ions can be oxidized to iodine, just oxidation of iodide ions to iodine. We need 2 here and 2 negatively charged electrons here. State sum is not required, okay. Use a half equation for the conversion of Cr to O72 minus to Cr3 plus. Now in this case, there's a special thing. I've got 2 chromium on the left side, 2 on the right, so I need a 2 here firstly. Then I can do my normal stuff. So add 7H2O, add water molecules, but then I've got 14H pluses, then add 14H pluses here. And then I need to add 12 negative, no, not 12 negatively charged electrons, because Cr has a charge of 3 plus, but now I've got 2 of them, so the charge is going to be plus 6. So I need to add 6 negatively charged electrons. There you go. 2 Cr, 2 Cr, 7 oxygen, 7 oxygens, 14 hydrogen, 14 hydrogens. Overall charge 12 plus on the left hand side, 6 plus on the left hand side, 6 plus on the right hand side. Use the answer for question 3.5, question 3.6, reduce overall redox equation. So then I need 6 electrons here, 2 electrons there, 6 electrons there, so I need to times this by 3. So I get 6i minus, I wrote the whole equation, 3i2 plus 6e minus, negatively charged electrons cancel out, and then I'm left with 6i minus plus 14H plus Cr2 O72 minus arrow 3i2 plus 2Cr3 plus 7H2O. Yeah, that's it. But there's one more thing. Or is there, actually? No, there's nothing. That's fine. That's in its final form. But in some cases, you've got H pluses on both sides, and you cancel them out. In some cases, you've got water molecules on the left and right side, so you need to cancel them out. But in this case, it's fine. So plus 6, 2i minus I2 plus 2 minus Cr2O72 minus plus 14H plus 60 minus 2Cr3 plus 7H2O, 6i minus plus 14H plus Cr2O72 minus to form 2Cr3 plus 7H2O plus 3i2. Perfect. Question 4. Explain the pattern in the first ionization use of the elements from lithium to neon. Stage 1, the general trend from lithium to neon, or to Li to Ne. So, first things first, first ionization energy increases across the period, right? More protons / increased nuclear charge and electrons are in the same energy level, hence no extra shielding. Stronger attraction between nucleus and outer electron. Then what I need to do is probably the most important part. It's the hardest part because general trend, you need to know the trends, obviously. First ionization energy increases, more protons / increased nuclear charge, electrons on the same energy level, therefore no extra shielding / similar shielding, strong attraction between nucleus and outer electron. But then stage 2, you need to look for deviations. So one of them is nitrogen and oxygen. Oxygen is lower than nitrogen, the first ionization energy, because the two electrons in 2p pair. And pairing causes repulsion. And then the repulsion means less energy to move electrons for lower first. Hence, oxygen has a lower first ionization energy than nitrogen, even though it should, just according to the trend, have a higher one than nitrogen. Stage 3, another deviation, beryllium and boron. Boron is lower than beryllium. The outer electron in 2p orbital is higher in energy than 2s. Lower because the outer electron 2p orbital is higher in energy than 2s, therefore it's got more shielding, atomic radius, therefore boron is going to have a lower first ionization energy than beryllium. Question 5. Calculate moles of nitrogen dioxide and chlorine in equilibrium mixture. Again, the method I like to use, and the ice method. I initial moles, C change in moles, E equilibrium moles. So I've got nitrogen dioxide, I've got chlorine, I've got NaCl, and I've got 1.50 moles of this, 1.00 moles of this. Mixtures left equilibrium, I've got 0.350 moles of this, adding 0.350. In this case I'm going to minus 0.350, but in this case for chlorine it's a 1 to 2 mole ratio, so I'm going to minus 0.350 divided by 2. So 1.50 minus 0.350, 1.15, 1.00 minus 0.350 divided by 2, 0.825. Given the expression for equilibrium constant Kc, Kc is square brackets products to the power P, so NaCl, 2 moles of that squared over the reactants to the power R, so No squared. And I've got chlorine, I've only got 1 mole of that, so that's not to the power of anything. Perfect. And remember Kc square brackets, because if you get that wrong and you do curly brackets, you get mixed up between Kp, or with Kp you get mixed up with Kc, and you're going to get the whole mark wrong, because it's 1 mark, you need everything to be right in order to get that 1 mark. Question 5.3. A different equilibrium mixture is prepared in a flask of volume of this at a different temperature. Our equilibrium mixture contains this much of nitrogen dioxide and this much of chlorine. For the reaction at this temperature, Kc is that. Determine the amount of moles of NaCl in this equilibrium mixture. So amount of moles of NaCl in this equilibrium mixture. So I want to find out, I want to rearrange this equation so I get concentration NaCl equals the square root of Kc times by concentration nitrogen dioxide times by, no, that's squared, that's really important, times by chlorine, concentration chlorine. So it's going to be square root of, now I can zoom back in, what am I working with? 1.32 times by 10 to the power minus 2 10 times by the concentrations. Now that's important. Concentrations of nitrogen dioxide and chlorine. Nitrogen dioxide, that's the moles, but the volume is that. Moles, concentration moles divided by volume. So it's going to be 0.850 divided by 800 divided by 1000, so 0.800 squared times by concentration of chlorine 0.458. Let me put it here, times by 0.458 divided by 0.800. So let's do that first. 1.32 times by 10 to the power minus 2 times by 0.850 divided by 0.800 squared times by 0.450 divided by 0.800. That's the number of that's the concentration of NaCl. I want the number of moles. Well, moles concentration of volume, so I'm going to do the concentration times by the volume, and I get 0.07. How many significant figures does it tell me? So 0.073 should be fine. Question 6. Use the results to calculate the MR of H2A. Okay, and there's even another calculation question. Okay, so this one, first thing I would do is ask myself, why would they give me the titration results in the table? Because they want me to use it, right? So I'm gonna have to look for the concordant titers. So these two, 0.1 centimeters cubed within each other. So it's gonna be 26.40 plus 26.50 divided by 2. That's the first step, identifying that you have to use the data in table 3. .45 centimeters cubed, and I'm told that a pipette is used to add 25 centimeters cubed of this much to a conical flask. So what I would do now is I'd find out the moles of sodium hydroxide. Yeah, am I doing that? Moles of sodium hydroxide, which is 26.45 divided by 1000 times by 0.112. No, it's not. No, it's not. No, it's not. No, it's not. I'm confused with a different question because usually it says a 25 centimeters cube sample, but this case says this much is added. So it's going to be then 25 divided by 1000 times by 0.112. That's moles of sodium hydroxide in there. Number of moles of acid, I divide that by 2 then because of 1 to 2 mole ratio. But then I want it in 250 centimeters cubed. And I know 250 centimeters cubed aqueous solution used to prepare this much of H2A. What I then do is, so I find out the moles, so 25 divided by 1000 times by 0.112. So in this case, this question, I'm not directly using this right now, I'm going to use it later on. So a lot of the times you have to use the value of the title right now, but in this case you need to use it later on. So then it's going to be number of moles of sodium hydroxide divided by 2 then times by 8, because I want 250 centimeters cubed. Then what I'm going to do is then do that times by 250 divided by 26.45. And then I get, wait, I've done something wrong clearly, because I'm not getting what the mark scheme is saying. 25 divided by 1000 times by 0.112 moles of sodium hydroxide. Okay, divided by 2 times by 8 . Oh, I don't times by 8. That's what I did wrong. I don't times by 8. Because then I know 250 centimeters cubed prepared using this much, but I want the MR of this. So then to find out the number of moles in that, then I do 1.40 times by 10 to the power minus 3 times by 250 divided by 26.45. Then that will give me the moles I actually want the H2A, 0.0132. Moles mass of MR, MR is mass in grams, so then 1.300 divided by 0.0132, and then I get 98.5 of the MR. Calculate percentage of certain using prepared experiment is 0.06. And I know the pipette use at 25 centimeters cubed. That's over 25 then. No 0.24%. 0.24%. Before adding the solution, I'm going to be writing the rough titration air bubble below the tap and the administered titration air bubble is not there. So remember, the air bubble increases the final burette reading of the rough titration. The idea that the air bubble takes up volume that would be filled by solution. Air bubble takes up volume that would be filled by solution. Suggests why this washing does not give an accurate result when you wash the inside of a conical flask with some distilled water. Does not react with the alkali / does not change the number of moles of alkali. Question 7, given the equation for reaction of titanium chloride and magnesium, so it's going to be I'm trying to call it. It's Mg. I don't need to state equation. Symbol equation Mg plus TiCl4 2Mg plus 2MgCl2 plus Ti, and then if I need a 2 here, yeah, 2Mg plus TiCl4 to form 2MgCl2 plus Ti. Roll the magnesium. Reducing agent. 2Mg plus TiCl4 to form Ti plus 2MgCl2. Calculate percentage by mass of magnesium oxide in this mixture. Magnesium oxide, what's that? What's that? Calculate percentage by mass of that, and I know mixture magnesium oxide, magnesium hydroxide has mass of that. So both of these things, this and that, have a mass of that. The mass of water produces 210 milligrams. So I can use the mass of water to calculate the moles of water. Then I can use that to look at the moles of magnesium oxide. Then I can do the total mass minus the mass of magnesium oxide. No, then I can do. No, then I use the moles of H2O, 1 to 1 molar ratio, that's the moles of magnesium hydroxide, Find out the mass of magnesium hydroxide. Do the total mass minus the mass of magnesium hydroxide to find the mass of magnesium oxide. Then mass of magnesium oxide of the total mass times by 100. I think that's what we do anyway. One thing I would do immediately is, because I'm going to use moles mass of MR, convert it into grams. So milligrams to grams, I'm going to divide by 1,000. Perfect. So in this case, I know total mass is 3.20 grams. I know that. Mass of water is that. So number 1, the moles of H2O, which is the mass in grams. So milligrams to grams divided by 1,000, 0.210 divided by the MR, which is 18. Then that's the number of moles. Well, first let's work that out. Let's not rush any steps. Do it step by step. Logically, 0.011666. It keeps recurring, 7. Then that's the number of moles of magnesium hydroxide. Then I can work out the mass of magnesium hydroxide. Moles and mass of MR, the mass of magnesium hydroxide is the number of moles in my calculator, which is that, times by the MR of magnesium hydroxide. So answer times by MR of magnesium hydroxide. Now I know, and I need to know magnesium 24.3. So times by 24.3 plus 16 plus 16 plus 2. Then I get the mass is equal to 0.680 grams. And I know the total mass is that. So I need to find out the percentage by mass of magnesium oxide. So I'm going to do that. 3.200 minus my answer, mass in grams. Then I get the mass of magnesium oxide, 2.52 over 3.200 times by 100. Inshallah, I'm correct, and I get 78.8%. Perfect. 78.8%. Allow 78.7 to 78.8. Perfect. So moles of the H water. Then you can work out the mass of magnesium hydroxide. Then you can work out the mass of magnesium oxide, and then substitute that in to get your percentage. Question 8. The following pairs of compounds, each in aqueous solutions, can be distinguished by simple test tube reactions. Give a reagent or combination of reagents that can be added to the solutions in each pair to distinguish between them in a single reaction. State was observed in each case. Sodium chloride and barium chloride. So the reagent for this case, and you can use text, I'm just going to write it down. So H2SO4, sulfuric acid. Observation with sodium chloride, no visible change. Observation with barium chloride, white precipitate. Sodium chloride and sodium carbonate, the reagent, if I use could use acidified silver nitrate. I could also use H2SO4 again. So use H2SO4, no visible change, and then sodium carbonate, effervescence. That's the end of section A.